Welcome to the community of
engineers, the change agents in the society.
We will continue our discussion on stresses, whereas stress is the internal resistive force of the body in response to the external force, which we used to term as the mechanical force. To represent stress, we require three information. So, stress representation needs the magnitude or the value of stress, the direction of the stress, and the plane at which the stress is acting. If we consider a circular rod, a rectangular cross-section beam, the stresses would be along three axes. Let's say we have a rectangular cross-section beam. The stresses would be along the three axes let's say this is x-axis, this is y-axis, and this is z-axis. Now in this axis is termed as the longitudinal axis, and the other two axes are known as the lateral or transverse axis. Now the longitudinal axis axis along the longest dimension of the component or body, whereas the lateral or transverse axis would be, or we may say, other than the longitudinal axis, other two axes are the lateral or transverse axis or axis along the minor dimension are known as the transverse axis. Now for the case of circular rod, the axis along the longest dimension is same as the longitudinal axis, since there are only one other dimension. Now this is as the radial axis. Now for the case of oblique plane, let's say we have a rectangular cross-section beam and this is axially loaded with a force P, and we pass a section at angle theta. Now here this is the angle theta. Now to consider the force acting on the oblique plane, we draw a free body diagram. In this free body diagram, let's say we cut the cross-section beam at the oblique section. Now the axial force is acting like this. Now because of the oblique plane, this force is divided into two components. One is labeled as F and the other, that is V. Now this F is the normal to the oblique plane, so this is the normal component, and this is the tangential which is parallel to the oblique plane. So we can say the F is the normal to the oblique plane, oblique section, and V is the tangential to the oblique section. Now the point to note is that because of the oblique cross section, the same force is divided into normal and the tangential or the shear force components. The overall force that will remain same. The P is going to be equal to F plus the V component, the shear component. But as a result, we are getting, because of the application of the force, now the axial force is converted into the normal component that will produce the normal stress and because of the shear force component, this will produce the shear stress. Now to calculate the values of this normal and shear stress, let's say the basic expression for the normal stress, that is sigma, is P over A. Now here in this case F is the P, so F component we can write this as the P cos theta, and same is the case the area because of the oblique section. Now this area is going to be A naught upon cos theta. So using these value in the basic expression, the value of normal stress at angle theta would be P cos theta upon A naught over cos theta. Now this we can write this as P upon A naught cos theta cos theta. This A naught is the original or the normal. Once there is no, the angle is, the theta value is 0. This is just perpendicular to the application of the force. So this is the original cross section area. Now we are calculating at angle theta. Now we can write this as sigma theta is going to be P over A naught cos square theta, or we can write this as sigma theta. Theta could be any value from 0 to 90. This is going to be sigma naught cos square theta. Now sigma naught is the value once there is the theta value is 0, the application of force is perpendicular to the plane. The plane is perpendicular to the application of the force. Similarly, for the case of shear stress, the basic expression for the shear stress, that is tau is equal to the shear force upon the area. Now here in this case, the value of the shear force value is P sin theta, and same A theta is going to be the A naught upon cos theta. Now using these values for the case of theta, we write this P sin theta upon A naught cos theta, or we may write this as P upon A naught sin theta cos theta, or we can write this sigma theta tau naught sin theta cos theta. Now this is the value once the application of the plane is parallel to the application of force. Now further we see that the normal stress for the case of sigma theta. Now sigma theta would be having maximum value at theta is equal to 0 degree, because cos 0 is going to be 1, and the sigma theta would be having 0 value at theta 90 degree, because cos 90 degree would be 0. Similarly, for the case of shear stress on oblique plane, tau theta. Now tau theta would be having 0 value once theta is 0 degree and 90 degree, and tau theta would be of maximum value once theta is 45 degree. Now if we consider the stress ratio for both the cases, normal stress and the shear stress, the sigma theta upon sigma naught is as cos square theta, and tau theta upon tau naught is going to be sin theta cos theta. Now in this plot, the horizontal axis showing the degrees from 0 to 90 degree, and the vertical axis is showing the stress value from 0 to 1. Now for the case of, let's say, the normal stress curve is going to be like this. This is the normal stress curve, and for the case of shear, the curve is going to be like this. Now this is shear stress curve. In this plot we can see that the maximum value for the case of normal stress, that is at 0, and once the oblique angle that is start increasing from 0 to 90 degree, the stress value is decreasing, and ultimately it ends up with 0 value at 90 degree angle. And if we see the shear stress values at 0, the shear stress for the case of the oblique cross section or oblique plane, it would be 0 at 0 degree, and once the angle is increasing, the shear stress value is increasing. The maximum shear stress value we are getting at angle 45, and after that again there is a decrease, and at 90 degree the stress value that is again 0. Now we will discuss stress under general loading conditions, and for that we take an arbitrary body. Let's say this is an arbitrary body made up of uniform material, and this is subjected to number of loads. Let's say the load P1, load P2, load P3, load P4, and so on, acting on this body. And because of these external loads, the stresses are produced in this body, and to evaluate the stresses which are built up because of these external forces, we take a cut section of this body, and we draw this cut section of the body like this on coordinate axis. Here this is the x coordinate, this is y, this is z, and further we take a small elemental area of this cut section of del A, and the stresses which are produced on this small elemental area are sigma xx tau xy tau xz, and the notations which we are following here, notations the first letter of the subscript shows the face on which the stress is acting, and the second letter indicates the direction of the stress. Like here, this sigma, the first x letter indicates that the stress is acting on the face which is facing towards the x direction, and the second letter indicates the direction of the stress. Likewise, this tau xy means the stress is acting on the face which is facing towards the x direction, and the direction of the stress is along y axis. Similarly, with this tau xz, the stress is acting on the face which is facing towards the x direction, and the stress direction is along the z direction. Now, for better visualization of the stress conditions at elemental area del A, consider a small cube of the side A. The E side of the cube is of length A. Here again, these are the three coordinate axes. This is x, this is y, this is z direction, and the stresses acting on the visible planes of the cube are, this is going to be sigma xx, this tau xy, this tau xz. Similarly, on the face which is facing towards the y direction are sigma yy, sigma yx, sorry, this is tau yx, tau yz, and the stresses on the face which is facing towards the z direction are sigma zz, tau zx, tau zy. Now again, here the first letter indicates the side on which the stress is acting. There it is x, means the stress is acting on the face which is facing toward the x direction, and the second letter is the direction of the stress. Now in this case we may write this sigma xx as single sigma x. Now for all the normal stresses, because the stress is perpendicular to the face, we may write as like this sigma x. Instead of writing sigma yy, we may write this sigma y, and similarly we may write sigma z. Now here in this cube there are actually 6 faces. So there are 6 faces of the cube, and on each face the 3 stresses are the stress components are acting. So it means there are total of 18 stress components which are acting on this elemental cube. Now considering the equilibrium conditions, like sum of F is equal to 0 means sum of forces along x-axis are 0, sum of forces along y-axis 0, and sum of forces along z direction are 0. Similarly, sum of moments is equal to 0 means sum of moment about x axis 0, sum of moment about y axis is 0, and sum of moment about z axis is 0. Now by considering these equilibrium conditions, we are reduced with nine stress components out of total 18 stress components. Now for further simplicity, let's consider for simplicity we consider a two-dimensional case, means one side of the only one side of the cube. Now on this cube the stresses would be like here, this is sigma x del A. A is the area of this elemental face. This is tau xy del A. Similarly, this is sigma y del A, this is tau yx del A, this is sigma x del A, this is tau x y del A. Here this is sigma y del A, and here this is tau yx del A. Now taking a moment about z-axis, the sum of moment about z-axis is equal to 0. Let's say we take moment about this pivot, and the distance or the length of this face is A. So taking a moment about z-axis, we get tau xy del A small a minus tau yx del A small a equals to 0. Now this is the stress tau xy, the first, and this is the second. Now this is in fact here, this is the stress which is acting on x face couple, and this is on y face couple. And if you see, this stress is acting counterclockwise, and this stress is acting on the opposite direction, clockwise. Now after cancelling these terms del A and small a, we are left with tau xy minus tau yx is equal to 0. Thus we are having tau xy which is equal to tau yx. Similarly, for other sides, tau xz is equal to tau zx, and tau yz equals to tau zy. So in fact we are left with we are reduced to only 6 stress components out of total 9, and actual total 18 stress components. So these are the stress components: sigma x, sigma y, sigma z, tau xy, tau xz, and tau yz. So we are having 3 normal stresses, and same we are having 3 shear stresses. Further, to evaluate the loading conditions and the point or the elemental area which is under consideration, the interpretations of these could be like this. Let's say we have a rectangular cross section beam. Let's say we take two beams which is subjected to tensile loading or the axial loading with load P in parallel, and we take a small elemental area. Let's say this is this elemental, this we consider as the beam A of rectangular cross section, and this is beam B rectangular cross section, and the point and the elemental area which is under consideration is oriented like this. And for the case of B, the orientation of small elemental area is like this. And if we take a larger view of these two, and for the case of beam A, the stresses would be acting still on like this, so means normal stresses on this orientation of the elemental area, the stresses would be of only normal stresses, no possibility of shear stresses. And if the orientation of the elemental area is like this, which is represented in beam B, and we take a large view, the stresses would be like this, so here for this case or in this orientation there would be normal stresses acting on all the faces, as well as there would be shear stresses acting on all the faces. This orientation effect we will also discuss later. Further, structural members or machines must be designed in such a way that the working stresses are less than the ultimate strength of the material, and this is known as the factor of safety, which is ultimate stress upon the allowable stress as factor of safety sigma u ultimate stress sigma low. Ultimate stress is the stress on which the material goes into permanent deformation or breakage, and allowable as a designer we allow that stress that should be minimum than the ultimate stress. So that is the factor of safety. Now the considerations why we consider this factor of safety. So general considerations for the factor of safety are: first, uncertainty, in material properties. Then uncertainty of loading conditions. Then uncertainty of analysis which are being performed, number of loading cycles, which is in fact fatigue. Then types of failure are the failure modes. Then maintenance requirements, and deterioration, risk of life and property, which is top of that. Further, it is very important to understand the difference between pressure and stress. Now, pressure we define as the external applied force on an object or body, whereas stress is the internal resistive force the object or body. Let's say we have a small cylindrical body and this is subjected to a external force, that is pressure, and as a result there are stresses in the body. Now pressure is the external force upon area, and the units are Newton per meter square, which is Pascal, and stress again is the resistive force upon area. Again, the units are same. Now further, for clear understanding, we say the pressure may be applied on fluids, whereas stress is applied on solid objects. This is pressure is acting only perpendicular whereas stress acts perpendicular as well as parallel, and the examples are the perpendicular stresses are the normal stresses and parallel are the shear stresses. Further, pressure is a scalar quantity whereas stress is a tensor quantity. And we have already discussed that it requires three information for the representation of stress, that is in the form of tensor, that is magnitude or the value of the stress, the direction of the stress, and the plane at which the stress is acting. Now further, pressure is always positive stress may be positive or negative. For example, a body is subjected to tensile load, so this will be positive. And if it is subjected to compressive loading, that would be negative. Further, pressure is an external force which acts on specific area of the object or body, and stress is an internal resistive force of the object on which pressure is applied to resist the deformation. With this we end of our discussion here.